Hello, my name is CP Joyce. I'm here today to talk about a, a really ancient device uh, dating back to the second century, basically. It's called the Armillary Sphere. I spent some time the last, I would say, 3 weeks uh, putting this device together. And I built it over a week's worth of time out of a sheer curiosity as to how time came to be measured in the centuries gone by. Back in the day, when the concept of time was yet to be invented into a clock as we know it today, the notion of time was merely a physical study of the happenings of the universe, basically. And so, sunrise to sunset would be a predefinition of what we today know as time. What you see here is what came to be, a device that has its foundations in Greece back in the second century BC. After that, the Roman synthesis and Chinese innovation, came up to make it a spherical device. And then between the 8th and 13th century, you saw a bunch of refinement happen with it. And in the 13th to the 16th century, it became to be known as what we see today, the armillary sphere. An armilla in, in Latin is a ring. So this device, as you can see, has a bunch of rings around it. It's built of several rings, each with a certain purpose. And so plural, armilla, armillae, is what this came to be known as in the version we know of it today. The armillary sphere has many functions. One of the basic functions is to determine what direction and what time the sun would rise at any position on the Earth, and at what time it would set. That's a very simple utility of the device. Lunar phases, the passage of moon through the nodes, and the ecliptic movement of the Earth around the sun are all equally visible. The One of the major functions here is to understand how the cosmos worked. Back then, since we didn't have all the devices we have today, uh, this was used to fit the model into the reasoning we had about the Earth being round, not being round, having an elliptic orbit, having a circular orbit, so on and so forth. So I'll explain to you what this device has. The concept of a circular celestial uh, you know, cosmos began with Plato's teachings. While he never had anything to do with building a device like this, a lot of the uh, interpretation of a spherical cosmos came out of Plato's teachings. So everything here is deeply rooted in his teachings. As you can see here in this device, right in the middle, you have the Earth, basically. You have the Earth right here. And while we all know the Earth actually rotates around the sun, but for the purposes of measurement, we place it in the middle here. We have the north-south meridian, which is where latitude is defined. It's easy to define latitude, as we know. Longitude, as many books have talked about, was a long-standing effort. Determining longitude, as easy as it may seem through GPSs today, was an extraordinarily complicated task back in the day. So this meridian here is the local meridian at any place on Earth. What you see here is a ring that indicates time. Beneath it is the sun's ecliptic. If you rotate this around, you will find that the sun is at its peak right there, and that's in summer on June 21st. Then comes the September equinox when it intercepts the 23.4 degree point. Further down, goes all the way down to December 21st, which is the lowest point on the sun's ecliptic, the shortest day. And come back up here, you'll come back to March, which is where it intercepts the 23.4 degree mark again. You'll also see the lunar phases here, where it intercepts the sun's ecliptic, which is again offset. The lunar orbit is offset from the sun's ecliptic by another 5 degrees, you'll find that these are the nodes that we refer to in both astronomy and astrology. These are the two nodes where it intercepts. You can figure out eclipses by positioning the sun at a certain point, seeing where the full moon will occur, and then having the Earth be right in the middle there, casting a shadow, which is where a lunar eclipse will be defined. For a simple application here, for any location, you first set the cradle to the latitude of the location. So right here in Chicago, we set it to, let's say, 42 degrees. And that we 1, 2, 3, 4. Set it to a 42-degree latitude. And once you have that set, and we position the sun on a date. This ring not only has dates here, as you can tell, it has constellations, Aquarius, you can see Capricorn, you can see Pisces. So the sun's position actually traverses through the various constellations. So let's say we position this in January, which is what it is today. So we position it on Jan 1. I'm just going to rotate this around. We position this on Jan 1. Now here we have the sun positioned on 1st of Jan, as you can tell. It's right here on 1st of Jan here. Rotate the ring around to know where it intercepts the equator. This is the Earth's equator ring, the equatorial ring right here. So you only see the sun rise above the equator. So as the sun comes up about here, as of today, it will rise at about 121 degrees. That's about approximately southeast in Chicago. It begins at about 121 degrees, and you can read the time of this location here, which is about 8 in the morning. Since we offset time in the US for daylight savings, it is about 7:10 instead of 8:10. So 7:10 is what the sun rose at today morning. And so you can read the time off here. You can read the direction, so you know exactly where the sun is at and what time it actually will rise. Now the sun the apparent motion as the Earth rotates, the sun comes up to mid-heaven, right up in the center of the sky, and it's winter, so it doesn't rise really high. It is pretty low if you compare it. It's not really up there in the sky as it would be in summer. It comes up here, passes through the meridian, and then begins to get lower. And as you can see now, on the other side, you will see it coming back down to set. And the sun will set, as you can tell, at this angle here, about 239 degrees. It will set, and it will set at about 4:30 Central Standard Time. So you will see how you can see the motion of the sun from point to point for any latitude that you position the Armillary Sphere for. Now, let's say you change it to a different day, and we pick up the sun and we move it to, let's say, a day in May. Position it to the 15th of May. Now, naturally, we know the days get longer, so the sun is now in May, and it'll rise a lot more to the northeast at 60 degrees. At 60 degrees, and it will not only rise at 60 degrees, it also then will set further off to the northwest. So it not only rises at 60 degrees, it will rise earlier in the morning at about 5:30 in the morning, basically. You rotate the sphere around for it to get to the sunset point. As it gets to the sunset point, you see where the sun sets. It'll set right here at about 310 degrees, and it sets at a time 7 o'clock in the evening, basically, is when it'll set. So you can monitor the sun's motion. If you understand that in summer, as you put it back up here for May, the sun's at a much higher angle in the sky as compared to winter. It comes straight up here. In summer, the sun's right up here at noon, whereas in winter you saw it was right down here. So it does come upwards, and it has a far bigger arc around the Earth, of course towards the south, but a far bigger arc around the Earth. Now let's change positions. Let's change the location to a place that is far more towards the Arctic Circle. Let's take location at about the Arctic Circle here. As you can see, position this on June 21st, and here you can see why in certain parts of the world the sun never sets basically at the peak of summer. Let's watch this happen. If you take this, the sun is on June 20th, and you'll see as you rotate the sphere, the sun goes around. Remember, there's the equator. There's the sun here, it never sets. This is for places really close to the Arctic Circle, right about to the North Pole or even to the South Pole. You'll see that the sun will rotate and stay up in the sky, it never sets. So there's a point. That's why for places like Norway, Sweden, or Denmark, you'll see long days and very little night. And anything above there, you pretty much see there is no night at all. Likewise, in winter, if you were to position the sun for a winter position, you will find that the sun will never rise in certain parts of the world around the Arctic Circle. So position this there. You see now, and never rise, the sun will remain beneath. It remains beneath the, it remains beneath, you see, it stays the horizon and never. Likewise, go down to a place close to the equator. Take a place close to the equator. You will find the variations. There's a winter day. The variations in day and night, winter or summer, are pretty much minimal. As you can see, even in the peak of summer, the sun, yes, will have a slightly longer day, but it is not as pronounced as somewhere in the northern hemisphere or the southern hemisphere closer to the poles. So this is one utility of the Armillary Sphere. As you position the planet, you can position every other planet here too beyond the sun and study the motion that the sphere can actually tell you. This is true north right here, as it indicates. That's the North Pole, the South Pole, that's west and that's east. That's the equator, the meridian at any location, the ecliptic, the sun's celestial equator, the Earth's celestial equator, the sun's ecliptic, and the moon's orbit, all positioned. That's the Arctic Circle here, and likewise you have the Antarctic Circle down here. So in one device, as this says, the entire universe in one instrument. It's a fascinating piece of technology, for its own time, back in the time when it was constructed, but it helped understand the workings of the cosmos. I hope you enjoyed this. Thank you very much.